The place you want to go is most definitely the stat menu again. And you're going to go over to tests. This is a hypothesis test. This most definitely is a hypothesis test. It's a test of a hypothesis: is my flu vaccine working? The hypothesis is that it is working. The other hypothesis is that it's not working. This test gives you the tool to decide which way the switch should go, yes or no. Now, you've got a bazillion of them to pick from. And when I say bazillion, I mean like 20. You have to root through which one you're going to use. Take a guess which one you're going to use.
Z-test?
It's definitely a Z-test, but not the very first one. Watch.
That'd be one prop.
Tell me why we're not going to use that one for a couple of reasons.
We only have one set of data.
Oh, that's true. Oh, okay, to L1, L2. Thank you, Elizabeth. Good for you. I wasn't even thinking about that. I was thinking I couldn't get past that and that. And definitely I couldn't get past that. It's asking me to give you what the population standard deviation is. Please. Come on now. Born yesterday. Now let's go to test again. Now do you remember when we ran confidence intervals, we had to use that guy called one prop Z int down here? Remember him? Guess what we're going to use now? One prop Z test! It's exactly the same test. It's your single-sided confidence interval, Aaron. But it's not called that. It's called a one prop Z test instead. It's TIEs. Nobody in the world, unfortunately, calls it a one-sided confidence interval. I wish they did. They don't. We're stuck with the language.
I'm not seeing what the difference is.
There is no difference. That's the thing. My point is there's no difference between a one-sided interval and what we're doing right now. There's no difference. I wish they would just call it confidence intervals and teach it as such. Nobody does. So I'm trying to teach it kind of as such, but still maintaining you guys getting the information you need to understand what the journals are saying. It is.
But how are the other ones two-sided?
Because when you run a confidence interval, you've got area on this side and this side, and you can either go out above or below that interval. Here, you're only interested in exiting one way. Does everybody hear Aaron's awesome question? It's a very, very good one. We could run this as a two-sided test. I have plans for us to run two-sided tests in here later on.
I'm sorry, I'm so...
Don't you be sorry, this is a great question. No, this is a fantastic question. This is a great question. The idea, though, is the flu vaccine makers don't want to test this. They don't want to test that. Can anybody see why they don't want to test that? That doesn't mean significantly less than 12%. It means significantly different than 12%. Why don't they want to test that?
It's higher than...
Because if it comes out on that side of the confidence interval, it means they're making them sicker than otherwise. Does that make sense? Yeah, so that's why we want to make this a one-sided test, because we want it to exit to this side. Great, it's a great question. Thank you for that. Yeah, it's very, very good. Sometimes all you're looking for is two-sided. This is not a good example of one that should be two-sided, though. It should be one-sided, because we want the vaccine to go this way. Is that fair?
Yeah, can you give me an example of what, like, something we're doing...
With two-sided?
Two-sided?
Can you hold? I want to make sure... Well, actually, everything we did before... No, I got what you're saying. Everything we did before was two-sided because we had no idea of the value in the population. So we just said, let's get a sample and then build a symmetric margin of error around it. So, right? We got a value, build a symmetric. So this 12% is probably the result of lots and lots of those. The margin of error is shrunken down so far now, it's at 12%. Now we want to see if our vaccine puts us outside of that 12%, but we only want to go to one side of it. Does that make sense? A lot of times they're used in tandem with each other. Great questions, Eric. Please keep them coming. No, they are. They're fantastic. I love the fact you're thinking about this. See the connections. There are definitely connections. Where did this come from? Lots and lots of studies. With a margin of error that is shrunken essentially to 0. Now we're trying to see if our sample, which is nowhere near a margin of error of 0, is escaped that 12%. Fair? Fairer.
Yeah.
Good. That's what I like to see. Fairer. This is not going to be crystal clear today. If it is, bless you. Bless you. It took me weeks to finally go like, okay, I don't think he's full of crap anymore. Dr. Mason. Love you, Dr. Mason. If you're watching this, you're not. But for years, I'm like, for weeks, I'm like, dude, what the hell are you talking? Alpha? The hell is that? And finally, I'm like, okay, got it. It's starting to sink in. And the way I finally did it was by constantly referring back to these curves. Now, 25 years ago, the technology wasn't there yet. Thank God it is now. We can use technology to help us. But I like always referring back to that curve to see where we land on it. So basically, Aaron, to answer your question one more time, this point right here is essentially a two-sided interval. We're just trying to see if we land to this side with our own interval. Cool? Good stuff. I'll put this back the way it was if it's okay with you guys. No, please always always ask those questions. They're fantastic. Helps us understand it better. Okay, so we're going to one prop z test. Are we okay with y? You never use anything with a z on it unless it also has the word prop on it. Prop stands for? Proportion. Always want to make sure you do that. So one prop z test. Does it look familiar to you? It should look ish familiar to you. It should look ishy familiar. And the reason it should look ishy familiar is because it looks an awful lot like one prop z int, where it asks for x and n. Yes, x and n. It's very nice. It does ask for something different. It asks for p with this strange rectangle next to it. I wish the TI didn't do this, but it does. What do you think that is? P with the rectangle next to it. FYI, it's not a rectangle. It's a zero.
It's a zero.
It's a zero. So what do you think goes up there, friends? 0.12, 12%. It's asking for what proportion value numerically is in the null hypothesis. So in other words, it's asking you, what am I comparing your data to? It's asking for this part of the calculation right here. So you tell it, 0.12. Now it says, okay, thank you very much. Because I now have that part, and that part of the calculation that I need. I've got those three pieces right there. It still needs that piece, and it still needs that piece. But all of that can be gotten from these two values right here. So that's when you tell it next, you say, oh, I got 101 out of 1,000 people get sick.
My numbers were in there.
They were.
Yeah.
Interesting.
I don't know.
That's pretty
Must have
bad.
been
Maybe,
playing with it.
maybe did you do a one prop z in?
Maybe.
Yeah, it would have carried him over. TI's kind of clever like that. Okay? The only thing you have to do now is make sure you pick the correct sign. See, so Aaron just asked about the two-tailed test. We don't want that. We want a one-tailed test, but then we have to ask ourselves, oh, is it left or is it right? And that's why I make you write these out. I make you write these out because I want you to just see that right there. And you see how it says, this is terrible TIEs. It says prop, not equal, less than, greater than. It's talking about the one in this. It's your claim. It's the claim you're making in the test. And the claim you're making in this test is that your vaccinated people are going to have less of a flu rate than the rest of the population. So mine's already set in the right place. You guys, if it's not, just make sure you grab it and highlight that middle one. Is that fair? It's TIEs, unfortunately. Believe it or not, Excel is worse. As far as the language goes, their language is even worse than this. Then you have two choices. You can calculate or you can draw. Let's do them both and you guys decide. Okay, let's do calculate first. So you scroll down and press enter. It's going to think for a couple seconds and it's going to come back with some results. Did anybody get an error? Let's fix the errors right now before we go any further. We're good. Okay. So you might recognize this, prop less than 0.12. That's just a restatement of the research hypothesis. Everything below this is a summary of your test. Does this look familiar? Z equals negative 1.848934, blah, 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 blah. Does that look familiar? Hopefully! That was a calculation we did right here. Yay! Does this look familiar? P equals. Does that look familiar? Oh yes, that does too, doesn't it? Yes. That's our P value. That's step 7 and 8 on your template sheet. The test statistic and the P value. Notice, and I get back to Brian, notice there's no 1.64, no 1.65 anywhere in there, because you don't need it. If you know the P value is 3.22%, you know you've exited over into the red region. Not exactly on the border, but over into it. Good, very good question, Brian. Do we answer your question yet about what happens if you land exactly at 5? We'll come back to it because we're in the middle of this. This, I don't know why it does this, it just gives you a restatement of what you already knew. It gives you P hat 10.1%, and it gives you 1,000. So, that's all that is. Good so far. So you get the exact same results using technology. Ask me questions right now. We'll get back to Brandon's question in a second. Ask me questions right now, if you have any right now.
So what is the, like, what would the field use, I guess, as the number value? Would they use the Z?
They always give you both of these.
Always both?
What you'll see is, they'll say something like, we saw significant results, and then in parentheses, P less than 0.05, comma, Z equals this, from experimental, not placebo. So you're going to see both of those. And the thing is, on that step 6 of your template, you see it says which distribution would you use? Z, T, chi-square, F? Those are each different distributions that are used depending on the context. Sometimes you'll see F equals 2.4, you'll see chi-square equals 16.32. We're going to see all these in this class as we go through the next 5 weeks. So the important thing that they're pointing to is, did this come in small?
Right.
If this came in small, the experimental effect appears to have had an effect. That's a good general answer for you. Fair, Brian?
Yeah.
Fair, good, good. Brandon did ask a fantastic question. His question is, what if the results came in right at 5%? Right, what if, this is 3.2%, it's close to 5, but it's not 5, it's rejection. Reject the null, right? What if that came in closer to 5%? Well, if you believe that what your results weren't a fluke, go sample more data. And here's why I say that. Here's why I say that, right? Here's why I say that. Suppose you ran the test again. You doubled your sample, okay? You doubled your sample. So you got 202 out of 2,000. Good so far? Now if you run the sample again, notice, you get the exact same p-hat value on a sample of 2,000. So you still get 10.1% of your sample got sick. But look at the change in the significance. You are now more significant because you're more standard deviations away. Now mathematically, the reason that happens is right here. This is why it happened. The difference here is still 1.9% down, isn't it? This is still 1.9% down because it's still 0.101 minus 12. This is still, but the standard error has now shrunk because this number right here got bigger. That means the fraction got smaller. You're dividing by a smaller number. That makes this fraction bigger. That's a lot of math, I apologize. When you have a fraction and the denominator of this fraction gets smaller, this number gets bigger. Dividing by a large number makes the whole thing more significant. So that's the idea of a larger sample size. I think I said that backwards. I think they came out sideways. But yeah, I said it right the first time. The idea is a larger sample size will increase significance because you're decreasing the standard error. It's getting tighter. That's why I referenced this before, Aaron, when I said this 12% technically has a margin of error. But it's been replicated hundreds of thousands of times, so the margin of error has essentially shrunken down to 0. This means that even a 0.1% difference will become significant. Practically, I don't know. I don't want to argue that. Statistically, yes, I do want to argue that. Because that's the only thing we can argue, right? We can only argue, did you land in the red or did you land in the blue? That's all we can argue in this class. This is why you guys are taking your degrees, to become experts in your other fields, to get the practical significance part, right? All we're learning here are the tools to get statistical significance. Believable? Perhaps. Getting there. Maybe. Brian, does that answer your question better? Brandon, that's the best answer I have. Go.
What if you can't sample more?
What if you can't? Then you farm out your results for somebody else to replicate it.
Okay.
This is why psychologists, sociologists, HDFS folks pore over the journals and replicate studies. This is why you also see the sometimes dangerous practice of collating studies into one large study. I forget, those are called something. Meta-analyses, I think they're called. When you get a whole bunch of studies and put them together, that's fine as long as every single one of those studies was done the exact same with the same controls. If not, you replicate it exactly the same and try to get the results again. Did anybody read that link I put last week, the truth wears out? I put that New Yorker article that I mentioned with the guy with the IQ tests. He was testing off the charts. I don't know if you remember me talking about that. Maybe Ghostbusters, we were talking about Ghostbusters and how this one guy was taking an IQ test, or not an IQ test, an ESP test. And he kept testing off the charts. He was getting, instead of 20% guessing, he was getting like 60 and 65% off the charts. Did they just stop there and go, this guy's a genius, he's got ESP out the wazoo? No, they tested him again, and again, and again. And guess what happened over time?
Yeah.
He came back down to 20%. That's why replication is so crucial. If you can't afford to do it yourself, Suppose you're doing crash tests on 1965 Lamborghini Countachs. Yeah, good luck with that one. Good luck. Can I borrow your 65 just for an afternoon? I'll return it to you. Won't be in quite the same condition that I got you. So what you do is you replicate a computer simulation, for example. That's what you're doing. Yes.
Okay.
Does that make sense? You see what I'm saying? So, and I want to come back to that computer simulation in a moment here too, because that is another valuable way of doing this. But that's right there, sir. That's one way of dealing with it, is replicate it in some way using the same controls. Thank you. Very, very good. Other questions? Such good question. I do want to share, speaking of what Brendan just asked, I was deciding whether or not to share this with you, but I will share it with you now, just because I think it's tied directly to what you just said, Brandon. Because honestly, this idea of exceptional cost does get in the way of good statistics. And you can see the can of worms it sometimes opens up, because then companies